everyone, we are Group 10 and our project was the underground garage. Urban cities are getting more and more populated, and with that the available spaces to park your car is decreasing. Some residential urban areas have no room for driveways, so you are forced to park out on the street, where you may not be able to find a spot, your parked car can get hit by other drivers, or may be susceptible to plenty of break-ins. To solve this issue, we will be designing an elevator for your car so that it can be brought from street level down to a garage below. This will keep your car secure while also decongesting some of these busy urban residential streets. Here is everyone in our group's team roles.
There are many machine design components that went into our underground elevator design to ensure that it was going to work properly and safely. One of the most important of these was the calculation of the safety factor, because this is the safety net of the device that will ensure there is no possible way of catastrophic failure. Engineers, even more than doctors, are held to a high degree of ethics because when something we design fails, many lives can be lost and massive amounts of damage can be caused. The following slides will detail the safety factor calculation for one of the folding arms that holds up the main platform of the elevator. The first step in determining the safety factor of the arm is to construct a free body diagram. This way, we can find the various forces that are acting on the component, which will allow us to conduct further analysis. The arm was modeled as a cantilever beam for simplicity. The point load on the device was calculated by combining the weight of an average car, approximately 4,300 pounds, and the weight of the steel platform, approximately 7,900 pounds, and then dividing that number by 4. This ends up equaling 3,050 pounds. From this analysis, we can see that there is a bending moment of 732,000 pound-inches on the arm. Now, we need to create a bending moment diagram to find the maximum and minimum moments the component experiences. The bending moment diagram is useful because it shows the complete range of forces that is experienced along the length of the arm. Analysis of this diagram clearly shows that the maximum moment is 732,000 pound-inches and the minimum moment is 0 pound-inches. This makes the calculation of the bending stresses rather simple. Now that we have determined the maximum bending moment experienced by the component, we can find the maximum bending stresses that it undergoes. The first equation is mc over I. M is the maximum moment, which is 732,000 pound-inches. C is the distance from the neutral axis to the outer surface, which is 6 inches. And I is the moment of inertia, which is calculated by the second equation on the slide, and ends up being 144 inches squared. The maximum bending stress is then found to be 30.5 ksi. Finally, we are able to determine the safety factor using the equation of yield strength over bending stress. From the manufacturer, we are given the yield strength as 36 ksi, so the minimum allowable safety factor is determined to be 1.18. It is important to take this value with a grain of salt, and it is usually recommended to round this value up to the nearest integer to ensure that failure will not occur even if the device is overloaded.
Our first SOLIDWORKS prototype kept the physical design in mind. So all the dimensions that we would use in our physical prototype, we brought over to the SOLIDWORKS prototype so we'd have something to base all of our drilling and cutting off of. Here we made a second prototype in SOLIDWORKS that kind of visualized what it would look like in the real world. To the left, you can see the green, which would be the grass or someone's yard, and underneath it is the cave-like thing that would be someone's garage that's built underneath their yard. And then to the right you see the road where if they didn't have this elevator and underground garage they would have to park. In the middle you can see the elevator slowly bringing the car down from the road into their garage, where then they can drive off and park into their garage underneath their yard rather than in the street.
The prototype design stage began when we were in the process of completing the bill of materials. At first, we focused on the sliders and decided that they will be 3D printed, since it would be the easiest process for the job. We also decided that everything will be joined together using nuts and bolts. Both of the plates are made from a sheet steel that has a thickness of 0.0299 inches. Similarly to how the image is demonstrating it, the side flaps were produced by making cuts in the sheet and folding the flaps to result in a 90-degree angle. The long slider hole was made by first drilling pilot holes and then using metal shears to cut along the length of the hole. After that, the hole was cleaned up using a Dremel tool.
Here are some pictures of our physical prototype. The net present value analysis is based on the full-scale production of this prototype, so it is estimated to be able to lift a 4,300-pound vehicle, have top lifting deck dimensions of 6.5 by 17.5 feet, and be made of A36 steel. For the purposes of this analysis, the lifetime of the machine was estimated to be 20 years. Table 1 shows the parts that may be necessary for the full-scale prototype, including steel plates, flat bars, round bars, industrial-sized nuts and bolts, and a hydraulic pump. The raw material costs come out to be $16,152.58. The production cost is estimated to be $1,720 based on hourly rates for plasma cutting and welding. The operational cost was estimated to be $754.47 annually, based on the calculated assumption that the machine would consume 572 kilowatt hours per year. The maintenance cost was estimated to be $2,000 per year, based on data from elevator repairs. The revenue was calculated to be $27,300 per year, assuming it would cost $7 per use for 15 people a day, 5 days a week. And the salvage value was calculated based on the A36 steel scrap prices of 10 cents per pound, and you can see this calculation in Table 2. The total salvage value is $2,148.03. Using an interest rate of 4%, the net present value of the machine came out to be $341,260.02.
So in the sustainability design analysis section, we started by choosing two main materials, aluminum and steel. And it's important to find their environmental impacts. Then we hopped on to SolidWorks and used the sustainability simulation to find the environmental impacts. And we found the carbon footprint, total energy consumed, air acidification, and water eutrophication. We found that they had similar air acidification and water eutrophication, and they had different total energy consumed and different carbon footprints. We chose to focus more on carbon footprints, and as you can see in the figure on your right, the aluminum had 250 kg CO2e and steel had 120 kg CO2e. And this is a main difference between the two materials. Then we went on finding the material financial impact because it's important. We found that aluminum had $46.5 US and steel had $32.1 US. So we chose these two factors to eliminate one material, and we found that steel had lower material financial impact, a lower carbon footprint for the future, and that's why we chose steel. And that's how we should choose materials, because we need to consider the sustainability part for our future.
And these are all the references used in the net present value analysis.